Hello viewers. Today we discuss about the design and performance analysis of fuzzy based hybrid controller for grid connected solar battery unified power quality conditioner. So in this work, you already know in previous videos we discussed about the unified power quality conditioner. The role of the unified power quality conditioner is voltage related and current related problems need to solve, right? So in the proposed model, we need to going to discuss about this control part, all design part. I will tell you right. Okay. So this is the grid part, and this one is non-linear load. Due to this non-linear load means rectified with RL parameter. Okay. So because of this non-linear load, the harmonics will be injected into the grid. In order to suppose, for example, this is not a pure grid. It is somewhat of distorted voltage signals. Okay. So I need to protect the voltage related problems. Here itself I need to solve. And then here itself I need to solve. And then the load related problems I need to solve here because of the shunt converter. Series converter is the role of the series converter is voltage related problems need to be solved, and shunt converter voltage current related problems will be solved. Current related problems is harmonic compensation and reactive compensation. These two are the shunt converters. So here I'm using solar with battery. These are the add-on microgrids. While we are connecting this one, I will tell you detailed below matter. Okay. So these are the simulation details regarding to how we are going to design our model. So whatever the simulation they mention, the same parameters I am taken here with the same voltage, same parameters, each and everything is accurate. So this one is the solar part, and this one is boost converter. How we are going to design this boost converter means with the help of the this one is the core for the R, L, C, D parameters. While how we are going to design this one means with the help of the some mathematical calculations. Okay, these are the mathematical calculations in order to design our model. Okay, for example, how much of L value? L value, how we are going to take 3 e power minus 3 means, suppose if you run this E file, for example, I am running this one. So here they mention after running this code. So we are already fixing the input and output voltage of the boost converter. The input voltage is 552 and output voltage is 700 and switching frequency is 10 kilohertz. Okay. So regarding to these formulas, we are fixing the values of the LCR parameters. Okay. LCR parameters means this one and this one. So how we are going to edit these values means with the help of the formula. Okay. In the same manner, bidirectional battery with a bidirectional converter having the same port. So this is the battery port. If you run this model, definitely we again getting the values of LCL. Okay. So again you need to take the values of L and C regarding to the same parameter. Okay. So these values is definitely matched with these values. Okay. So in this way, we can design the boost and buck boost converter for the requirement. Depend upon the requirement only, we need to design all these things. We can change the values also. Depend upon the design only, we are finding these values. Okay. Suppose if you change the output voltage, automatically values will be changed. Suppose if you take input value variation also, the output the parameters will be changed. Okay. Depends upon requirement only, we are fixing these values. So Regarding to this one, these are the topics. Now going to discuss about the controlling part. And this one is the series controller and shunt controller, and this one is the series controller. In here we having switches, right? So switches definitely require gate pulses. How we are going to generate the gate pulse means with the help of the control strategy. So I am using here synchronous reference frame theory as a control scheme to generate the accurate reference signal generation. That is, reference signal generation is must and should for our designs. That plays a major role. Okay. So for generating the voltage reference signal, we are using this control strategy. This control strategy is taken from this model. This is the control strategy taken from here. Okay. So we are giving back the load voltages and sending in voltages, and we are converting into ABC to DQ transformation. And then with these calculations, we are going to generate the pulses required for the series voltage source converter. So in the same manner, I generate each and everything. Across here, you need to see what is the main problem here is we need to get to the zero magnitude. Then only we can get the accurate reference signal magnitude, which is required to turn on the series converter. Okay, here. You need to observe this one. This one is the omega t. Okay, definitely that will be required in this manner only. The injected parameter reference signal will be like this way. Okay, and this voltage will be 230 into 415 into root 2 by 3. Okay, nearer to 38.856. Okay, so and why we are connecting like this way means it is injecting the voltage. Okay, one terminal is connected in series and another terminal is connected to the series compensator. So the series compensator, why we definitely connected in this way means we need to inject the add-on voltage, right? Add-on voltage, how we inject the add-on voltage means with this connection only it is possible. Suppose if you connect series connection, it's not possible. Okay, that is the problem. Series connections means either step down or step up. This is the connection way. Okay. Suppose in order to add on the additional voltages means with this connection only we can get the add-on voltage. And the grid side, I am taking voltage sag, swell, and harmonics with imbalances also. This case is already shown in this diagram. So they taken voltage sag, swell, harmonics in this case. So for that purpose, I am just taking all these cases. So this is the voltage sag and swell in the harmonics. Okay. So in the same manner, I am taking the voltage sag, swell, harmonics. So this is sag, swell, and the harmonics. When we zoom it, you can easily understand. Okay, this is the harmonic in the time part. So the overall running time period is 3.5 seconds. Okay. So this is voltage imbalance. Each phase of the voltage will having different magnitudes, right? That is the voltage imbalance. And this voltage sag, voltage swell, and voltage harmonics. So whatever the grid generating disorder signals is reduced or compensated by the series compensator. And then the load can get the accurate constant load magnitude, okay, or voltage by injecting the voltage injection here. This is the voltage injection. Suppose if voltage sag, voltage swell occurring here, that is quite opposite to the proposed one. That is the advantage of the design. Then I also mentioned the load imbalance condition. Load imbalance means one phase of the load will be disconnected. Okay, one phase of the load will be disconnected. I will show you. So in this particular time period, I am just disconnecting the load. Okay, this is the disconnection of the load. This is the sending end current, shunt injection current, and load current. So load actually generating non-linear load, right? So non-linear load will be like this way. So we need to inject the shunt currents, then it will convert into sinusoidal voltages. Okay. So this is the proof for the design. So this is the injecting currents, this is the non-linear load, and this one is the series current. I mean, the series generation side grid current. Okay. So this grid current is isolated between the isolated for phase 8 only. Why? Because to create load imbalance, right? So for that case, I am just disconnecting one phase of the load for short interval, 1.2 to 1.4 time interval. At that time, how the shunt compensator can inject the currents in order to protect the grid. Okay, that is the main thing. For that purpose, we are designing in this way. Okay, and regarding to solar parameters, initially I am using 0 to 2 time period 400 Weber per meter square, and then at third time interval I am increasing the radiation to 1000 Weber per meter square. This is one case in the design. Okay, I just changing the radiation, then how it will be act like we need to see, right? So for that purpose we are using voltage, current, over all these things will be shown related to what design. When all this will be happening, voltage side, voltage will, at that time, the grid voltage, grid power and grid reactive power. Definitely grid having both active and reactive power, right? So this is the proof. At voltage sag, voltage swell, harmonics, imbalances, in any case, the waveform will be like this. Finally, the battery voltage and current. Battery showing this minus means is discharging the uh, voltage. Okay, simply discharging the voltage. So in this way, we can add on the voltage to the grid. Our solar and PV both will help you to feed the power to the grid at required time interval. And this one is the DC link voltage. At any case, okay, voltage variable, voltage in all these cases, including also, you can get the DC link. How this DC link voltage can maintain constantness? With the help of the shunt converter. So this one is the shunt converter. The shunt converter can be controlled by the DC link control strategy. This one is the DC link control strategy. This DC link control strategy can maintain the DC link and the DC link voltage constant to the required level. Okay, that means this voltage is maintained nearly 700 to 720 in between the range. Okay, that is the control strategy we made here to maintain DC link voltage constant. So then this one is the exact DC link voltage after using of the control strategy. Okay, so here are the all overall design regarding to the PQC integrated with the solar battery with the fuzzy controller. Fuzzy controller where we implemented this. Instead of this PA controller, you need to design the fuzzy. And then we need to make rules to run the model. So that is the thing. Uh, when we talk about that one, I will clearly explain to you. So this is the overall view regarding to the UPQC with different control strategies. So many things will be available here, but due to short time, I will explain this shortly. Okay, I will end up this here.